Okay, let's start. First of all, thank you for giving me this opportunity to present my work that is accepted in WACV 2025. Today, I actually want to explain about my paper that is related to multi-class prompt-driven anomaly detection under a domain shift or distribution shift. So today, first of all, I will give you an introduction about visual industrial-based anomaly detection, what is visual anomaly detection, and what is the goals that we want to achieve. And after that, I will talk about the most important related work about my work in anomaly detection. And after that, I will talk about what is my contribution and our work in our project. And at the end of the day, I will explain some qualitative and quantitative experiment and result that we achieve. And before that, I would like to mention that our work is in collaboration with Dr. Afgah and Nilufar Alipur from Clemson University. So what is visual anomaly detection and what are the goals in visual anomaly detection? In visual anomaly detection, we want to achieve two main goals. First of all, for each input data that we have, we want to see whether this is belong to anomaly or not. So this is a basic binary classification that we want to achieve. And in visual anomaly detection, also we want to look through to the data that we have and localize the area of the anomalies in input data that we have. And because of the nature of this problem, generally we have a large number of normal data in the training, but in the test we have data that belongs to the normal and anomaly classes, and we want to use some indicator in residual or in feature level, abstract level, or even in the input and image level to be defined to be used as an indicator for us to achieve the goal of anomaly detection, which is image-based anomaly detection or uh, actually pixel-based anomaly detection. So basically, in our work, we want to achieve two goals. For each input data that we have, we want to actually say whether this input data is belonging to the anomaly or normal. And also for per pixel, we want to see what are the areas of anomalies in input data. And in relation to the application of anomaly detection, specifically visual anomaly detection, it has been different application in industry, in autonomous vehicle, in medical image analysis, or in different industry for designing visual inspection system, we can actually adopt a visual anomaly detection. So let me start from one of the conventional way in machine learning and computer vision to do anomaly detection. As you already know, we have a vanilla autoencoder in machine learning actually concept that generally we feed our data to our autoencoder that belong to the normal data, and we actually train our autoencoder in such a way that it learns the distribution of the normal data, and in the inference time we use some indicator to compute the residual error between the input image and also the reconstructed image, and we use some kinds of actually error calculation in pixel level to define what is the anomaly and the location of anomaly. So this is the conventional way to actually compute the anomaly in visual anomaly detection. And also, in addition to the pixel level, we can also define anomaly indicator in feature level by calculating the error in feature representation between the normal feature and also the reconstructed image and the reconstructed feature, and use it as an indicator for anomaly. But in addition to this line of study, which is very conventional in doing anomaly detection, we have different line of study that is based on reverse knowledge distillation or First of all, it is based on knowledge distillation. But what is knowledge distillation, anomaly detection, and reverse knowledge distillation, anomaly detection, that my work is based on them? First of all, let's define what is knowledge distillation and how it relates to conventional autoencoder to do anomaly detection. The main goal of knowledge distillation is related to compressing a network to a lightweight network, to have a network for any task that you have. But in our case, we want to leverage the concept of knowledge distillation to do anomaly detection. In knowledge distillation, we feed our normal data. I want to remind you that in training anomaly detector, we generally, because of the nature of the problem, we only have a large number of normal data, and we only have a very low amount of abnormal data, and we try to only learn the distribution of the normal data, and then we actually, in the inference time, we use a residual error between the normal and reconstructed error to distinguish whether the input data is related to the anomaly or abnormal. So this is the case also in studies based on knowledge distillation. In even these studies, we only use the normal data to train our network. And then in the inference time, we use some kinds of error between different feature map to actually achieve to the goal of anomaly detection. So let me explain you how actually this knowledge-based distillation work for anomaly detection. So basically, in knowledge-based anomaly detection, we have a teacher network that is already pre-trained on a large number of source data. Let's imagine that this teacher network has been pre-trained on ImageNet. So to train our student network to learn the distribution of the normal data for our main task, which is anomaly detection, we distill the knowledge from the teacher to a student in different feature representation in different stages of a network, and try to enforce the student to mimic the representation of teacher in different stages. And when we actually train in such a way, this student will learn the distribution of the normal data, and in the inference time, we compute the error between the different representation of a student and teacher to actually calculate the heat map of our anomaly. So this is how it works. In the training phase, we feed the normal data to the frozen teacher and also the student that we want to mimic the representation of teacher, and we use the error between the feature map of a student and teacher as an indicator for doing anomaly detection in inference time. And this is how actually knowledge distillation works. But after this vanilla knowledge distillation, we have another line of research. We try to address some of the issue of these and challenges of these baseline of knowledge distillation, which we call reverse knowledge distillation. In reverse knowledge distillation, we try to actually compress the data of the teacher and feed it to the student so that the student can mimic this representation and the knowledge of the teacher. And one actually advantages of the reverse knowledge distillation compared to the vanilla knowledge distillation is that not all information in a teacher is valuable for us to be distilled to the student for knowledge distillation. So we try to compress and get rid of some redundant information, redundant features from the teacher to the student. And because of this reverse knowledge distillation proves to work better compared to vanilla knowledge distillation. And one interesting thing, if you actually see this network and compare to the autoencoder, is in the fact that if you actually pull a student to the right position, you can see this is very similar to our autoencoder. But the difference is that in reverse knowledge distillation, This is another paper that first actually published in CVPR 2022 based on reverse knowledge distillation that proved that it works very well compared to the conventional autoencoder or even the baseline knowledge distillation. So, I mean, if you pull this student to the right way, you can see that this is very similar to the architecture of autoencoder, but with some advantages that it proves that it works. First of all, as I mentioned, it tried to compress the data. And in addition to this, in autoencoder, we actually train a network from scratch. But now we have a good source of data, and the data and information that we have is actually are incorporated in a frozen teacher that has been pre-trained on ImageNet. So we want to use and leverage this source of information for our knowledge distillation. And we use a hierarchical of a representation in different stages of the teacher and compress and get rid of redundant information for our knowledge distillation. And by this way, we try to actually enforce the student to mimic the representation of the teacher for normal data. And as I explained, in the inference time, we use the difference between the heat map of the teacher and the student to do anomaly detection. So I explained this related work because my project and my paper actually are based on reverse knowledge distillation, and you should actually know about these backgrounds and how reverse knowledge distillation. But one disadvantage of this reverse knowledge distillation is that there are single base model. It means that, for instance, if we have different classes, different objects, this actually anomaly detection doesn't work. And for each class, for each object, we need to actually save the weights of a student and this bottleneck independently. And we do not have one all-in-one actually anomaly detector. So we want to address this issue. And now let's go to my proposed method that have two goals. The first goal is the thing that I already explained. We want to have one all-in-one anomaly detector that work for different classes, and we do not need to save different weights of the different classes and different objects and do anomaly detection for each of them per time. We want one all-in-one anomaly detector. And another important challenge of conventional anomaly detection is the issue that most of the time because of the nature of the training of these anomaly detection in unsupervised way, and because they only see the distribution of the normal data, they try to mimic the distribution of the normal data. But when it comes to the test, and when more importantly, we have a distribution shift in the test and inference time, these a network cannot distinguish between the distribution shift and also the abnormal data, and the performance of these anomaly detector drops significantly. So in our work, we want to address also this distribution shift problem. But how we do that? So this is the proposed architecture of my network that try to address these two issues that I explained at the same time. So first of all, for the first issue that I explained, to have one all-in-one anomaly detector, we try to design different class-aware prompts and initialize them randomly and try to learn them so that when we feed our data in the inference time with different classes, it can distinguish between different classes, and it can actually reduce the interclass interference between different classes so it works well. So what I mean is that we want to actually give a hint, provide a good source of hint for the network to be leveraged. So in the test and inference time, when we feed our abnormal and normal data under different classes, it has some knowledge that this image and input is related to a specific class, and it will reduce the interclass interference between different classes to better reconstruct the normal data and to better actually has a better generalized anomaly indicator for anomaly detection. So as I mentioned, for different classes, we design different prompts. And then at the same time, in the encoder part of our network, we try to design some integration module which actually is incorporated from different sequential cross-attention network. And we feed these prompt to our different stages of a cross-attention network and provide a hint about the type of the classes of the input. So how we actually learn this hint to actually give a guidance to our network? To actually learn this prompt at the same time with our loss function for anomaly detection to do anomaly detection, we actually concatenated feature representation from different stages of a network and added regularization to regularize our encoder to distinguish between different classes. So these are different cross-attention in different stages of our network. We feed hint and we feed this hint to different cross-attention that we design to be incorporated in our encoder. And then we concatenate different features in different stages of a network for output of the cross-attention and concatenate these features all together and feed it to the classifier to actually distinguish between different classes. And by doing so, we try to learn these hints. So at the test time, when we feed our network, we actually can provide a hint for our encoder to distinguish between different classes and reduce the interference in issue between different classes and work for different classes. So this is how actually we actually come up with the idea to make a single class reverse-based anomaly detection to all-in-one multi-class anomaly detection, given the prompt and hints that we provided for the network and we learned it during our training. But as I mentioned, another issue and challenge that we have in conventional anomaly detection is related to the robustness. They are not robust when it comes to the inference time under different distribution shift. So to actually make our model robust, we try to actually leverage the idea of adaptive instance normalization layer. In adaptive instance normalization layer, when we actually normalize data and calculate mean and sigma and also use the parameters of beta and gamma, these actually normalization and these mu and sigma can somehow reflect and model the style of the input image. What I mean is that if we have a network and we have an adaptive instance normalization, we can adjust beta and gamma of adaptive instance normalization according to the style of the input data. For instance, if we have a normal data and we change the distribution or style of this normal data to have a different brightness, then we actually can see that the beta and gamma and what it is the style code of this adaptive instance. The style code of this adaptive instance normalization would be changed. So our idea is that we incorporate these layers into our decoder, and then we try to actually adjust these style codes so that we actually make our decoder robustify against different distribution shift. So how we do that? To do that, we actually use a domain adapter. We train this domain adapter to generate domain-invariant representation in terms of identity parameter and style codes. And these style codes then feed to different adaptive instance normalization in our decoder. So after we train these domain adapter, and this domain adapter in the inference time generate our adaptive instance normalization parameter, which we call a style code. We feed this style code in the inference time, which actually are robustify against different distribution shift. And by this way, we make our decoder robustify against different types of distribution shift and domain shift. And to do so in the training phase, we actually use some synthetic data augmentation such as solarize to make it robust. So this is how actually our idea work to make our anomaly detector robustify against different distribution shift. And this is the overall loss function. As I explained, in a normal reverse knowledge distillation, we have a KLD versions loss function to actually enforce the student decoder to mimic the representation of the teacher in different feature representation, different stages of a network. So this is a main loss function for anomaly detection. And also we add two loss function in relation to learning these hint or prompt for our network, and also in relation to training these domain adapter and learning domain invariant representation from the perspective of this domain adapter. So the overall loss function incorporated of the main knowledge distillation loss function for anomaly detection and two proposed loss function of our contributions. But how we validate our method? We validate our method based on two settings. The first one is what already other actually paper adopted. It is based on in-distribution evaluation. It means that we do not have any distribution shift between the training and test set, and we follow the conventional benchmark in MVTech or VISA, and we adopted AUC to report the image level and pixel level AUC in different actually classes of our benchmark. And as I explained, we use two benchmark to evaluate and gauge the performance of our proposed method against distribution shift and in multi-class anomaly detection setting. So these are our results based on MVTech benchmark, based on anomaly detection and anomaly localization. It means it actually perform per image detection and per pixel anomaly detection, and it is reported based on AUC. And as you mentioned, as you see in many classes, we outperform most of the multi-class and single class anomaly detection, and some of them are multi-class and some of them are single class anomaly detection. You can see that in both setting of single class and multi-class, we outperform the SOTA detectors. And also another contribution of this paper, as I mentioned, is related to the robustness. So we actually curate benchmark based on MVTech and VISA, but under distribution shift. And to do so, we actually curate this distribution shift based on brightness, contrast, and Belair Gaussian, and also Gaussian noise, and gauge the performance of our detector under this distribution shift. And also we evaluate other state of the art such as Uni-AD or GNL, which is actually a state of the art in multi-class and single class anomaly detection, to be compared with our method. And also this is a result for VISA benchmark and VISA dataset. That is another benchmark that we adopted in our paper for our comparison. And this is also qualitative example that how our model work under distribution shift. And as you can see that the localization of anomaly are more accurate, for instance, compared to Uni-AD method in relation to different classes. Our localization is more accurate and does not any, it has less error compared to the others. And these are also some other results in other benchmark. This is a MVTech benchmark, and this is, I think, VISA benchmark. So in conclusion, in our paper, first of all, our paper are based on reverse knowledge distillation. We actually add two novelties in this baseline. First of all, we make it into all-in-one anomaly detection to work for different types of anomalies, and we actually do not necessarily need to save different ways for each classes. And second, we also propose domain adapter and leverage the idea of adaptive instance normalization, and use a style code to be adapted on the fly to make our model robust against different distribution shift. And also we actually benchmark our ideas under two data set, under in distribution setting and also out distribution setting, to evaluate our method.